Welcome back, guys. We're on to our second topic, which is identifying redox reactions with oxidation numbers. Now, as per usual, everything is cumulative. So what we did in the first lesson is, of course, going to apply again. So ultimately, this starts to go into why those oxidation numbers are so important. And when you look at a chemical, and check how it changes from being on the reactant side to the product side, you'll see that there are situations where it'll either gain or it'll lose electrons. That should sound very familiar from previous lessons we've done. Okay, now reminder to you, of course, don't forget about this, please, is oxidation is always going to be a situation where the oxidation number increases. In other words, even though that seems counterintuitive, this is a situation where guaranteed you are losing electrons, right? And you can see by the equations that are given to you there that we have in both circumstances listed electrons being lost and electrons being lost, hence oxidation. Okay, vice versa. If you keep on going and we go into, I'm just going to change here a second, make that green. Okay, so let's keep going on into reduction on the other hand. Reduction, which again, recall from before, is that situation where you end up gaining electrons. Leo Ger, right? Nothing unfamiliar there. When you gain electrons, your oxidation number goes down, right? So oxidation number is going to decrease. Now, check out what you got going on below here. Similar type situation that we have our gain of electrons. So we have them as a reactant on both sides, okay? Now, don't lose sight of this. When you undergo reduction, the oxidation number becomes more negative, right? So it's going towards the negative side. Vice versa, when you undergo oxidation, the oxidation number becomes more positive. I'll show you what I mean. This is a table that we've looked at before. Notice that we have a circumstance with oxidation that the numbers are becoming less negative, right? That's how we know that electrons are being lost. Vice versa, with reduction, the numbers are becoming more negative. In other words, electrons are being gained. Keep that in the back of your head because having those numbers straight are going to make a huge difference. I want to relate this back to oxidizing agents and reducing agents as well. So first of all, keep in mind that the oxidizing agent is always undergoing reduction. Remember, those seem somewhat opposite, right? So the oxidizing agent always undergoes reduction. Vice versa, the reducing agent is always undergoing oxidation. Don't lose sight of that, okay? So if the oxidizing agent is gaining electrons, then the oxidizing agent has oxidation numbers that decrease. If the reducing agent is losing electrons, then it's going to have an oxidizing agent number where the oxidation number increases. Keep in mind, there are situations where reactions are not redox reactions, right? And in that case, there is no change in oxidation number. Well, that happens in quite a few reactions. This unit is about redox reactions, so of course that's our focus. Okay, let's start to look at some examples and how this applies to actually balancing redox equations. It's really important that you can make some sense out of this, guys, because we're going to apply it again into tomorrow's lesson. So to consider this scenario, how do we use oxidation numbers to show that we actually are dealing with a redox reaction when we combust methane? And step 2 there, please, is I want you to identify the OA and I want you to identify the RA. Let's start by just getting a good balanced reaction. So combustion reactions, going back to your different reaction types, We have methane gas, CH4 gas. If you don't know where that is, look in your data booklet, or what that is rather. Look in there, you'll find it. Combustion is going to be reacting with oxygen gas. Now, for this particular one, it does not say that it's in a bomb calorimeter, which means we're going to assume that the water being formed is going to be in gaseous form. H2O gas. No big deal, first step. Super familiar. Don't worry about balancing right now. The whole point of this, where we're headed to in tomorrow's lesson, is we'll balance based on oxidation numbers. So leave the balancing at this point. Okay, assigning oxidation numbers. Go back to what we talked about in yesterday's lesson. Common oxidation number should go first. So that includes hydrogen, for example, +1. Oxygen here shouldn't instantly get a -2 because it is as an element, which means it's 0. It's not part of a compound. Okay, go to carbon dioxide. In this scenario, well, this is part of a compound, so it gets the number -2. Go to water. This one's nice and easy. Hydrogen gets +1. Oxygen gets -2. That means we need to figure out the oxidation numbers of carbon in both of these. Go through the logic of it. Methane, going back to the beginning, has a net charge of 0. We have 4 times the +1. That's +4. What balances out a +4 and -4. You start to get into a habit with oxidation numbers where you might not have to show as much work. It's up to you. I'm not going to mark your algebra work. If you need to show it for you to get them right, then you better show it. Okay? But if you can do it in your head, awesome. Go to carbon dioxide. Carbon dioxide, we've got 2 times -2. That's a -4 total. -4 is going to be balanced out to get to 0 by a +4. Okay, that's the beginning. Once oxidation numbers are up there, you need to see how they've changed. So we have to compare the same elements and see how it changes. For example, check out hydrogen. Hydrogen is +1, whether it's a reactant or a product. No change, okay? Leave out hydrogen. But look at carbon. Carbon is changing, on the other hand, going from -4 all the way to +4. That's a significant change. How does it go from one to the other? Well, it actually loses 8 electrons for that to happen, right? It's going from a negative number to a positive number. It's losing electrons. Think about from a number line perspective. -4 goes to 0, goes to +4. From here to here is a change of 4. From here to here is another change of 4. And that's where I got the 8 from. Okay? So we lose 8 electrons per every atom of carbon. When you lose electrons, that one is undergoing oxidation. Okay? Look at the next scenario. Oxygen. Oxygen goes from an oxidation number of 0 to over on the other side, the product side, oxidation numbers of -2. That's a change. So we're going from 0 to -2, and this one's the same. Think about what that means. To go from 0 to -2, it is going to gain, and it is gaining 2 electrons per an oxygen atom. Anytime you gain electrons, you are undergoing reduction. Okay, that means that we've now just gotten the ability to figure out the oxidizing agent and the reducing agent. My reducing agent is going to be what's undergoing oxidation. In other words, the reducing agent is that methane. Don't just write the carbon, write the whole compound that it's a part of. Vice versa, the oxidizing agent is what is going to be gaining electrons, undergoing reduction. In this case, that is our oxygen gas. Remember, the Ra and the Oa are always going to be reactants. They're never products. That's something from earlier lessons as well. If the color helps you, consider what's going on here. The OA is what is going to be gaining electrons. In other words, we go from 0 to -2. That's a gain of electrons. Undergoes reduction and is the OA. Vice versa, the carbon is losing electrons from reactant side of -4 to product side of +4. If it loses electrons, it's oxidation. That means it's the Ra. Remember, guys, this is step by step. So this step will be built on in tomorrow's lesson. Okay, let's try another one. Check out this example. Exact same process, except I give you the equation this time. It is absolutely not balanced. Don't worry about the balancing yet. Your job is to assign oxidation numbers, then find the OA, and then find the RA. And once again, we'll focus on the RA being in green and the OA being in yellow. Okay, do the simple ones first. Oxygen, part of a compound, is -2. Simple. Hydrogen, H plus, +1 charge. Hydrogen, there's 5 of them, but each one has a +1. Oxygen, -2, hydrogen, -1. This chromium tells you its charge. It's a 3+ charge. So write that +3. Hydrogen, +1, oxygen, -2. Go to this last one here, right? Ethanoic acid. We've got +1 for the hydrogen, -2 for that oxygen, -2 for this one, +1 for the end. Okay, those are the simple ones, the common oxidation numbers. Now start to go to the others. We can figure out that chromium, and in fact, this is something that we had last time, this same actual example in your previous notes. So I'm just going to assign the oxidation numbers quickly here. Chromium's going to be +6. Carbon over here is going to be -2. Over here, we're going to have oxygens with 0 and with 0, right? Think about the logic of where this comes from, that +6. This one with the carbon, I'll go back to again just to talk about. We've got 6 hydrogens, that's +6. Then I add the -2 of the oxygen, I'm now at 4. How do I balance out a +4? Well, with a -4. But I have to split that into 2, -2, -2. Again, if you can't do this in your head, then you need to write it out. Show the work, okay? Same thing when we get to this last one with the ethanoic acid. Hey, check it out. I've got -4 with my oxygens, and I've got +4 with my hydrogens. -4, +4, that's already 0. That's why I put zeros on those carbons. All right, see what's happening here. My oxygens are -2 as reactants, -2 as products. No changes, leave them alone. My hydrogens, +1 as a reactant, +2 as a product. We'll leave them alone. So that puts us to the chromium. Look at the change. It's going from here to here, going from a +6 to a +3, which means the only way that it decreases in oxidation number is if it gains electrons. How many? Well, it's going to gain 3 electrons per an atom. Vice versa, look at the carbons. We're going from a -2 to a 0. To go from -2 to 0, from a negative number to a more positive number, the only way it can do that is by losing electrons. How many is it going to lose? 2 of them. Lose 2 electrons per an atom. The one that gained electrons is undergoing reduction. The one that lost electrons is, of course, undergoing oxidation. Okay, keep in mind what's what here. Don't get mixed up. The OA always undergoes reduction. It gains, all right? From +6 to +3 is a gain in electrons. The RA always loses electrons, undergoes oxidation. From -2 to 0, that is a loss of electrons. So finish this thing off by writing out what's what. My OA is going to be the dichromate Cr2O7 2 negative, and my RA vice versa is going to be that C2H5OH, the ethanol. There it is, folks. Whatever gains electrons is the oxidizing agent. Whatever loses electrons is the reducing agent. That's it for this lesson. I want you to absorb that, try the questions. The one that you should be trying for this one is number 3 in that weekly assignment number 2. Make sure you can make sense of it before we move on to the next step, which just builds completely on these first two lessons. Have a good rest of your day.